So here's the conclusion of 1999 AP exam question number 4, part D. So the situation was they gave us this information about function f of x and its derivatives at 0, and then they gave us the derivative of g right here at the end of the problem statement. In part D, it wants us to show that g double prime, the second derivative of g, is equal to this. So if we start with g prime of x, what I notice right away is that I have a function of x right here times another function of x right here. So when I take g double prime, I'm going to have to use the product rule. So by using the product rule, my second derivative for g is going to be the derivative of the first function that we see here. So the derivative of an exponential is going to be the same exponential, and then because we have more than just an x in this exponent, we're going to have to finish a little chain rule and multiply by the derivative of the inner function that we see in this exponent. So here's the derivative of the first function times the original second function, which would be 3f of x plus 2f prime of x. And then we're going to have to add to that the original first function of x, the original form of the exponential function, and then times the derivative of the second function. Now, we don't have to use any product rules or chain rules or anything inside this set of parentheses. This 3 is a constant, so I'm just going to copy it into my derivative, and then the derivative of f of x is going to give me an f prime of x. So I have 3f prime of x, and then add to that, similarly, the 2 is a constant, so I'm just going to copy that into my derivative, and then the derivative of f prime of x is going to give me f double prime of x. Now what we're trying to do is we're trying to show that this second derivative is equivalent to what they gave us here at the beginning of part D. To make this big ugly expression look more similar to this, I think I'm going to distribute into my sets of parentheses here and then see if we can refactor this a little bit, because we don't have two different terms in this form of g double prime, and we have two great big terms in our current form of g double prime. So I'm going to do some distribution. Let's see, I have a negative 2e to the negative 2x that I'm going to distribute into this. So if I do negative 2 times 3, that's going to give me negative 6, and then I'm going to have that exponential piece that's distributed in, and then I'm going to have an f of x on the tail end of that. If I distribute this term into this piece inside the parentheses, negative 2 times the 2 is going to give me a negative 4, and then I'm going to have the exponential that's distributed in, and then the f prime of x tacked on at the end of that term. I'm also going to distribute this exponential into this quantity, and that's going to be a little bit easier. No numbers are going to change. I'm just going to end up with an e to the negative 2x on each of these terms. So I'm going to have plus 3 e to the negative 2x f prime of x when I distribute into this piece, and then when I distribute it into the second piece, I'm going to have plus 2 e to the negative 2x times f double prime of x. Now if you look at this current line, we have 4 terms, and there really are 2 terms that are like terms. This term right here and this term right here are like terms because the prime on the f matches, right? They're both f primes, and then the exponentials match. So if I have minus 4 of these terms here, plus 3 of them there, I'm going to have minus 1 of them total. So if I go ahead and write out a new line, I get minus 6 e to the negative 2x times f of x. So the first term stays the same, but I combine these 2 like terms, and I'm looking at minus 1 e to the negative 2x times f prime of x. And then the last term is going to stay the same. It didn't have any terms that we could combine with it. So we are looking at a form for our derivative, our second derivative of g, that now has 3 different terms. We have 3 terms inside this set of parentheses. So it seems like maybe if we could do some factoring of a common factor between these three terms, we might be able to make it look like this. And if you think about it, the common factor is the exponential piece. So if we factor the exponential out of the three terms that we're looking at from the previous line, we're going to have minus 6 f of x, which is what we were supposed to have for the first term inside the parentheses, and then minus 1 f prime of x, which is what we were supposed to have for the second term inside the parentheses, and then plus 2 f double prime. So factor the GCF out, and you do have the exact form of the second derivative that we were asked to develop. So we've now proven that our second derivative is equal to what they gave us. Now the secondary question here is, does g have a local maximum at x equals 0? So does g have a local maximum at x equals 0? I'm going to quickly refer back to something that I'd done in a previous video from part C. We computed g prime of 0 in part C in order to develop the equation of our tangent line. And we figured out that g prime of 0 is 0. So the derivative of g, this right here, is equal to 0 when x is equal to 0. That means x equals 0 is a stationary point for g, right? 0, when put into the derivative, makes the derivative 0. Therefore, x equals 0 is a stationary point, a value of x that makes the derivative equal 0. So I'm just going to note that on this screen, okay? G prime of 0 equals 0. What we want to know is whether or not we have a local maximum at 0, and then to somehow try to justify our answer. Normally what we do to figure out where we have a local maximum is we try to build a sign chart for the first derivative. So that sign chart for the first derivative of g would look like this. You know, it'd have a split value at 0. Now what we'd have to do is we'd have to find a way to determine the sign of g to the left of 0, the sign of g prime to the right of 0. And we would see if we had a plus here and a minus here, the function would go from increasing to decreasing, leaving us with a local maximum at 0. In this case, we don't really want to waste our time doing that. What we have access to right here is g double prime. What I'm going to do with a little bit of space that I have at the bottom of this screen is I'm going to compute g double prime of 0. G double prime of 0 is going to be e to the negative 2 times 0 times negative 6 f of 0 minus 1 times f prime of 0, and then plus 2 times f double prime of 0. If I go ahead and take the values that we were given up in the problem statement here, so they're kind of up at the very top of the screen right now, f of 0 is 2. So this is 1 right here, right? And then I'm going to be looking at negative 6 times 2, and then minus 1 times, well, f prime of 0, that's right here, that's negative 3, and then plus 2 times f double prime of 0, which is 0. Now you might be wondering what the benefit to having g double prime of 0 is. I'm going to compute the value of this, and then we'll try to discuss where we're taking this. This would be negative 12, and this would be plus 3, and then that's plus 0. So negative 12 plus 3 would give us negative 9, times the 1 leaves us with negative 9. So g double prime of 0 is negative 9. So what we know from this is that we have a stationary point at the x value of 0. What we know from g double prime of 0 equaling negative 9 is that our function is concave down near 0 because the second derivative is negative. So what that means, if we have a stationary point and we're concave down, means our graph is going to have to look like this. Stationary point at 0, horizontal tangent line, and concave down at and around 0 because of the negative second derivative. Because the first derivative is 0 and the second derivative is negative, the only way that the function can look at the x value of 0 is like this, and that would indicate a local maximum at 0. And what we're using here is we're using the second derivative test. Normally we go with the first derivative test, which I was setting up and explaining the logic of back here. But in this case, it's easy to find the value of the second derivative at 0. And we can go ahead and realize that since the second derivative is negative, our function's concave down. meaning we have a local maximum at 0, and what we're using here to prove that is the second derivative test.